Right, we're carrying on with this never-ending light worksheet. Right, a light ray can undergo total internal reflection. Right, basically what that is something like this. There's your block. What happens is, let's use that. A light ray comes in, where it hits that, that's the normal, and this is the angle of incidence, and if you've this angle is greater than the critical angle. So let's go through that again then. Right, and the ray comes out. Let's do it this way. So it comes in and it goes out. That is the refracted ray. This is the angle of refraction. Right. This is the angle. This is the angle of incidence. This is the incidence ray. It is the incidence ray. Is that the right word? Or is it? No, incident. That's the angle of incidence. Right, okay. Now, if this angle here is equal to the critical angle is where total internal reflection occurs. So what's going to happen is the ray is going to come in, and if it's equal, you'll get some running along the boundary and some reflecting back. So does that make sense? So it goes that way. When I equals the critical angle. Now what happens when I is, which color should we use? No, let's use that. So when this angle is greater, you get the full ray reflecting. This is called total internal reflection. Right. Now we're gonna discuss that in a bit. Let's just move that. Ooh. Right, that's done anyway. Let's go back. Right, state two uses of total internal reflection. Right, there's a few uses, and learn the full sort of wording. Optical fiber for what? For communications. Communications. What's the other use? Endoscope for doctor. Optical fibrae, optical fibers for decorative lamps, right? And then safety reflector, okay. And you can have a prism in or for binoculars, binoculars or periscopes, right? Any one of those. Describe the conditions required for total internal reflection. Okay. So first of all, the light has to travel from a more dense or more optically dense, let's use the word optically dense instead of dense. It's a better phrase. More optically dense medium to a less dense medium. Right. And the angle of incidence, the angle of incidence. So let me get that word right. It's an incident. Yeah, it's incident ray by angle of incidence. The angle of incidence is more than or greater than the critical angle. Right, try to learn that. The conditions for, actually quite a good question that. Because you can actually make notes of the mark scheme. Okay, right, okay, here we go. Now this is, the diagram shows a light ray entering a glass block. Let me put that up. From air, and then, so this is air. Oh my god. This is air. And this is glass. So this is perpendicular, so you've got no refraction. It hits this. That line is called the what? Can you remember? Starts with an N. Right. Right, and then right. Okay, so draw the line of the normal line. We've done that. Measure the angle of incidence. So right, look, this here is the incident ray, and this here is the one that you've got to measure. This is the angle of incidence. That's what you've got to measure. So you'll draw that and you'll measure that. They've given a range between anything between 24 and 30 degrees. Basically what they're saying is 26, 27. Okay, that's quite a big, that's fair enough, that's quite a big range. It's unusual. Right, the critical angle of the block is 40. So right, let's do it this way then. So the rays coming in, the angle of incidence is less than, so it's gonna then come straight out. Yeah, so this is what's happening. It comes in, because this angle is less than 40, it's between 24 and 30, the ray is going to come out and it's going to bend, it's going to let me draw it here. There's your normal, there's your incoming ray, incident ray, because this is, just say 30 degrees, and if it was 40 degrees you'd get, or more than 40 degrees you'd get total internal reflection. Because it isn't, what happens is the ray comes out but it bends towards, so this angle here, the angle of refraction is less than 30 degrees in this case, right. So you have to, oh, so sorry, why am I lying to you? This is air, I keep forgetting, this is air here, right? So the ray is going to reflect away, it's to refract away, it's going to bend away, so this will be, I don't know, just say for argument's sake 35 degrees. Yeah, so it's going from a more dense to a less dense, and I've still not internalized that, but we'll get there eventually. State the equation linking critical angle. Again, this comes up so much, you've just got to learn it. N is the refractive index, this here is N, critical angle is C. Calculate the refractive index of the glass block. So we know sine 40 equals, it's only a 2 marker, but we're going to get into the physics habit of doing everything. We write it out, substitute in its raw form, then we rearrange it, and the answer is 1.6. Right, okay, let's keep going. State what is meant by refraction. What is refraction? Let's write this down. You've just got to learn them. Just parrot fashion, learn them, pick up the odd marks, and then see where it takes you. Yep. This is when waves change speed when they change the medium. So basically what they're saying is when it goes from a glass block to air, it's going to change speed and it will change direction as well. Right, the angle of refraction of the ray is 33. Right, so what they're saying is this angle here, you have to measure it 33 degrees. This is a good question, this. It's January 2020, paper 1. January 2020, paper 1. Yeah, question. So no, this is just, this question here is on this worksheet, but the actual question on the paper is question 7. It's a really good question. Print it out and physically do this. And then so the ray is bent towards the normal. That's it. In the water, that's it. We're not worried about this bit here, so ignore that. In the water. State the formula linking refractive index. So we've, right, let's write that down. So the refractive index N is sine infrared. Infrared. So sine incidence, sine angle of refraction. So this is I and this is R. So look at this formula here. Right, so let me write these two formulae down. So we said N equals the critical angle is 1 over N, and N equals sine infrared. That's how you can remember it. So these two formulae are useful. They seem to be repeating a lot, so just get them into your memory. You lot are young and you can handle it, so just crack on with it, mate. Right, show that the refractive index is about 1.3. So we know sine 45 degrees, where did that come from? From here, right? Divided by sine R, which is 33 degrees, which is this one or this one that we drew, yeah? Okay, and when you do that, you get 1.30. They tend to work to 2 decimal places or 3 sig fig, 3 significant figures. Okay. The torches move below the surface of the water. The light from the torch is incident on the water surface at an angle greater than the critical angle. Whoa. So what they're saying now is, this. They put the torch here. Oh, what on earth's that? Right, so now we're shining a lot. My God, did I just do that? No, you don't want to delete you. Let's move you there. So what's happening is we're going to shine a light. No, not that way. We're going to shine a light in that direction. That's the angle of incidence. Right. The light from the torch is incident to the water at an angle greater than the critical angle. Explain the meaning of the term critical angle. Right. This is where the angle of incidence is the angle of incidence is the angle of incidence above which total internal reflection occurs. Right, so what we're trying to say is this: the angle's coming in, right, and if this is bigger than the critical angle, you get total internal reflection. If it's equal to the critical angle, it'll run along the boundary that way. So it has to go in the slower medium. So this is the more dense, and if it's more dense, it has a lower speed. Right, don't worry about that, just learn that. This is where the angle of incidence is above the which total internal reflection occurs. That's the definition that they've given. Right, link the formula linking critical angle and refractive index. We've said that there. It's this one. Right, so sine C equals 1 over n. Calculate the critical angle of water. Assume that the refractive index is. Right, so we've got sine C equals 1 over 1.3. Sine to the minus 1, 1 over 1 point. These are the 3 steps they want you to do. Don't just jump straight onto this one. Okay. Right, let's do this last bit and then we can finish this video because it's 20 minutes. A ray of light leaves the torch. Oh, okay. I didn't need to draw that up there, did I? Look at that, eh? Banksy. Who needs GCSE art? Anyway. We've said 50. Okay, we know at 50 degrees you're gonna get, or above 50 degrees you're gonna get total internal reflection. Okay, at 50 degrees it's gonna run along the boundary and you're gonna get some reflection. Right. Right, okay, so let's get rid of that. That was something else. So it comes in at 55 degrees, it bounces back, it totally internally reflects at 55 degrees. So those are your 2 marks. Straight line reflected downwards from water surface, correct angle by eye. So you're going from water to air. Yep. That's it. 2 marks for that. Right, so roughly that way. So but they'll measure it by eye, rather than protractor, but maybe if you can use a protractor. Right, we're going to call it quits there.